Hello and welcome back to my GCSE Science. This video is about chemical analysis and specifically chromatography. Now we did look at chromatography early on in separating mixtures, but in this video we're going to look at it in a bit more detail, look at calculating RF values as well as how we would go about doing required practical 6. So first of all, just a bit of a recap. Chromatography is a method for separating mixtures. It's particularly good at separating several dissolved substances from each other. So for instance, in this example we've got a blob of ink. We place it on a pencil line that goes just above where the solvent starts, and as the solvent rises up the paper, the different substances dissolved in the ink will separate out. These are two possible results from a chromatography of some sort of ink pen, for example. Can you tell what the difference is? Well, of course, in this case we can only see one substance that's red and that was deposited here on the paper. In this example, the ink contained many different colours. Each was deposited at different distances up the paper. So this is a pure substance, and this is an impure substance, otherwise known as a mixture. So chromatography can be used to identify whether a substance is pure or not, and that's one of its applications in day-to-day life, such as in the chemical industry or, for example, in forensics. One thing you may not know yet about chromatography is that there are several different types of chromatography. This example is paper chromatography, but there's also gas chromatography, something called TLC, which is using a thin layer of an absorbent substance on a piece of plastic, and other types that you don't need to know about. The thing that makes them all chromatography is that they are methods of separating mixtures, and critically that they both have a mobile and a stationary phase. In all versions of chromatography, the mobile phase is the substance that moves. So in this case, the mobile phase is the solvent, which for this example is water, but it might be ethanol or some other kind of solvent. In gas chromatography, the mobile phase would be a gas, etc. The stationary phase is the part of the chromatography that doesn't move. So in this case, the stationary phase is the paper, because it doesn't move, and the water moves up the paper carrying the dissolved substances. So the way in which chromatography separates substances is by the mobile phase moving across the stationary phase. And in paper chromatography, the substance that moves the furthest up the paper is the most soluble substance. This is because substances are separated based on how attracted they are to each phase. The most soluble substances are more attracted to the mobile phase, which is the water, and so they stay in the water for longer and therefore travel further up the paper. The less soluble substances are less attracted to the mobile phase and comparatively more attracted to the stationary phase, so they get kind of dropped off sooner. So not only does paper chromatography allow us to separate, for example, different coloured inks from a pen, but it will also tell us which of those inks are more soluble than the others. Now let's look at how we can calculate something more accurate and comparable from chromatography. And this is with something called RF values. RF stands for retention factor, but this is not something you'd need to know. So just remember that the RF is a ratio of the distance moved by the substance you're interested in compared to the distance moved by the solvent. So this is an example of a result that you might get where we started at this line, which was our pencil line that we drew originally. These are each of the three substances that were mixed into the original sample, and this line was drawn at the end to mark how far the solvent moved, which might have been water or, as I said, another solvent like ethanol. So in order to calculate this RF value, we need to measure the distance travelled by each of these substances and the solvent. So for this particular result, we can calculate 3 RF values, and let's number them so we know what we're doing. So for number 1, we want the distance moved by the substance. If we look at the ruler, let's focus on the centre of the substance each time. So in this case, I'm going to say it's about 1.5. The distance moved by the solvent is 9.7, and the calculator gives us an RF value of 0.154639, etc. We'd normally be asked to give this to a specific number of decimal places, such as 2 decimal places, so we need to round this to 0.15. Because we have centimetres on the top and the bottom, we don't need any units here. This is because it's a ratio and the units cancel out. So the RF value is 0.15. Have a go yourself at doing the RF values for 2 and 3, pause the video and come back when you're done. Done it? Okay. I would say that 2 went about 3.7 centimetres and the solvent is the same distance, 9.7, and that gives us 0.3814, which is rounded to 0.38 if we go for 2 decimal places. Finally with 3, I'd say the middle goes to about 8.2, and that gives us a calculated value of about 0.84536, and so we round that to 0.85 because the second digit here is a 4 followed by a 5, so we have to round the 4 up to the next number up, which is 5. So there we are. RF values are important because they should always be the same if you do the experiment in the same way, with the same substance and the same solvent. But each substance will have its own RF value in different solvents, and each different substance will have different RF values within the same solvent. And this allows us to compare it with other samples, for example substances we know that either we or other people such as scientists or doctors have tested before. And it enables us to identify unknown substances, which makes it really useful in chemical analysis in industry, as well as in forensic analysis in police detective work, and for you in your practicals in the lab. It also tells us the relative solubility of each substance, with the smaller numbers referring to the substances that didn't travel as far, and the larger numbers referring to the substances that travelled much further. The maximum would be an RF value of 1, in which a substance travels the whole distance that the solvent did. Okay, well now let's have a look at what's required for your practical. So in this practical, you're expected to be able to use paper chromatography to separate and identify a mixture of food colourings. You'll be given an unknown mixture of food colourings, which is X, and you'll be given several known substances, which are the A, B, C and D spots. So you'll carry out the chromatography and measure the distance that's travelled by each of the spots A to D, and you'll compare these against your unknown mixture of substances to see which food colourings are in your sample of X. So to start with, let's just look at what we've got here in this apparatus. This is the beaker that we're going to use as our container, and we've got our solvent at the bottom here, which is water, filled up to about 1 centimetre high. Over here we've got our filter paper or chromatography paper, which remember is our stationary phase, and this would be a glass rod which we tape the paper to so that it stays in position and it hangs at the top of the beaker down into the water without it falling in so that the spots go in the water. So first of all, with your blank piece of paper, draw a horizontal line about 1 centimetre up from the bottom of the paper and make sure this is in pencil. It's important that it's in pencil because if it was in ink, then the solvent might also dissolve the ink and it will mess up your chromatography. But pencil doesn't dissolve in water, so it's a good thing to use as a reference point. Then using your pencil you can just mark out little X's to show where each of the spots are going to go. And then you use a small glass capillary tube, which is a very thin glass tube, to take a small sample of each of the colourings and put them on the 4 spots here for each of the known colourings A to D. And then finally on the 5th spot you're going to put your unknown colouring, X. Make sure that when you actually use the capillary tube to apply the spot, you don't let it spread out too far, as that might interfere with the results. Then before putting the paper into the beaker, add your water to about 1 centimetre depth. Then having taped the paper to your glass rod, slowly lower it into the beaker, making sure that the pencil line with the dots on it doesn't go into the water. This is really important again because if all of the dots went into the water, they would just dissolve in the water and the chromatography wouldn't work the way you expect it to work. So this is how it will be set up, and the key things to make sure is that the pencil line is above the level of the water and that the sides of the paper don't touch the beaker. And then all we've got to do is wait for the water to travel up the paper, carrying the spots with it. and you're going to wait until it gets at least 3/4 of the way up the paper, and try to be really careful not to disturb the beaker while you're waiting. When you're done, carefully remove the paper from the beaker, and as soon as possible, draw a line with a ruler to mark how far the water went up the paper. This is going to be your reference for the RF value. Then you'll need to leave your paper to dry thoroughly before you go any further. Now it's time to do the RF values as we did before. Remember that the RF value is the distance moved by the substance compared to the distance moved by the solvent. So the distance moved by the solvent is going to be the same for all four, but the difference moved by the substance or the spot is going to be different for each of them. So let's go back and see what we've got. Okay, so first of all we'll measure the distance that the solvent travelled, and we can see if we start the line at 0 here, we've got 9.5, that's 9.7 centimetres. In the table we've been asked for it in millimetres, so be careful with units, that's going to be 97 millimetres. If you're given units, make sure you write down the value in the correct units, but if you aren't given units, remember it doesn't really matter what units you use as long as you use the same units for both types of distances so that they cancel out. Okay, now A has gone the shortest distance, and if we look at the centre of the spot, that goes to, I would say, 1.2, which is 12 millimetres. B has travelled to, I would say, in between 2.4 and 2.5, that's 2.45, which in millimetres would be 24.5 millimetres. You may not be expected to be that accurate, but I think this is quite clearly in between, so I'm going to go for 0.5. Next we've got C. Remember to measure from the centre of the spot, and I would say that that goes to 5.8, which is 58 millimetres. And finally D travelled 8.15, because it's in between 8.1 and 8.2, so that's going to be 81.5 millimetres. Okay, I think after earlier you should be able to calculate the RF values for each of those. So have a go at doing that now. And these are the values you should have got. If you haven't got those values, then first of all check your calculation on your calculator, and second of all check your rounding, especially with this one. Okay, and finally we need to match up our unknown substance X with A, B, C or D. And hopefully what you should quite easily see is that we have the same colour for spot A and it's travelled the same distance. Spot B is not there in X. We have something in X that we didn't have in A, B, C or D. We don't have C in X, but we do have D. So we had A and D in X, but not B and not C, plus one other unknown substance. So out of the 4 colourings we did know, 2 of them were in X, and X had 3 colourings in them, but one of them was not one that we had a reference for. And that's all there is to it. So remember, chromatography is a method used to separate different substances that are dissolved in a liquid. Remember that chromatography always needs a mobile phase and a stationary phase in order for the mixture of substances to separate. An RF value is used to calculate the relative distance moved by the substance that you're interested in compared to the solvent that you're using. And RF values of a particular compound is always the same in the same solvent, which allows us and people in the chemical industry to use chromatography to identify unknown compounds. Thank you for watching, and see you again on the next video in chemical analysis about testing ions.